Hi everyone, and welcome to the fourth module in our Advanced Heat Pump Control Training for Radiant Heating and Cooling series. In this module, we're going to be looking at how to properly design a heat-cool distribution system for a geothermal application. In particular, we're going to be focusing on the considerations we need to take into account for a well-designed radiant heating and cooling system. So we'll look at the mechanical design elements, and we'll also look at the control elements. From a control perspective, we're going to go into greater detail in the following module, which will be Module 5. And that's when we will uncover all of the advanced control features that are in two of our Tekmar products, the House Control 406 and the TekMar Thermostat 557. So in the next module, we'll be focusing on the control side of our Tekmar products and how we can use those features to optimize the geothermal system. But I don't want to put the horse before the cart. Remember that even the best controls cannot compensate for a poorly designed distribution system. So let's get to the nuts and bolts of it first, and then we'll cover the controls next. The outline for this presentation is to bring up the hydronic design considerations, namely our entering load water temperatures. Then we'll look at radiant floor design and second stage heating. Now normally we can't satisfy the building needs with a radiant floor only. We do need to introduce second stage heating. And that means we're going to be requiring mixing. So we'll talk about the concept of mixing and how we can design and control that. Next, we'll talk about radiant floor cooling. And we'll introduce what the limitations of radiant floor cooling are. Remember, we can only address the sensible cooling load. We can't remove humidity with a chilled floor. So we'll be looking at what we need to do for a well-designed cooling system. We can't rely on radiant floor cooling alone, but it certainly can provide a large base load amount of cooling that'll reduce the load on the forced air system. So then we'll look at our forced air cooling and what we need to consider there. And lastly, we'll introduce some zone control. That's going to be our TekMar Thermostat 557. So we'll just introduce that control to you before Module 5, in which we will go into greater detail and depth on why the 557 is an excellent control choice for a geothermal radiant heat cool application. Let's first take a look at the hydronic design considerations. So of course, when we are talking hydronic design, one of the major benefits is the ability to zone a space. So as we've talked about before, every room in a building is going to have some unique heating and cooling needs, and that will depend on its location, if it has exterior walls or not, how much window area it has, what the occupancy is like. So one of the major attractions when we're talking about a hydronic distribution system is that it is relatively easy to zone. So we can easily customize the space conditioning for individual zones within our building. So zoning allows us to increase comfort while saving energy by heating or cooling based on current conditions. And we did introduce the concept of indoor feedback and zone synchronization in Module 3. So zoning gives us that ability to save energy by delivering heat only where we need it, in the amounts we need it, and not to put heat in rooms that potentially have low occupancy, or because of the solar or equipment gains in that room have lower heat needs than the other zones within the space. Zoning is really easy to do with hydronics, and we will design the hydronic distribution system based on the individual needs of the zones. So this is an example of a house layout where we have a bunch of different zones, and we'll look at one possibility for our zoning layout. So here we have the same layout, but now we've overlaid colors on top of it, showing you how someone might choose to zone this space. So what needs to be considered when you're zoning a home? Well, the things you look at are the occupancy of the room. So what are the owner requirements and occupancies like? What's the architectural layout? What are rooms that have inside walls versus exterior walls? What are rooms that are open concept, and so it doesn't make sense to try and zone rooms within an open concept layout? The other thing we can look at is glazing. So zones that have a lot of window space and might experience a lot of solar gain. You might want to zone those separately from rooms that do not have the same solar gains because they will have different types of needs. So more zones means a higher initial cost, but more opportunity for savings and comfort. So the savings part is because we're only putting heat or cooling into the rooms that need it in the amounts that they need. So instead of treating everything as one big blanket zone, even though they have different occupancies and needs, we can deliver the right amount of heat where it needs to be delivered. So let's look at the zoning that we've shown here. You can see we have one very large yellow zone, and that's because this area looks to be an open concept type area. So here it wouldn't make sense to try and zone these spaces separately because you have no doors, so that the heating is going to be moving freely throughout those zones. Other zones that we have shown here are media room, which would be zoned separately. Utility room, now this typically would see a lot of equipment heat gains, and so we want to make sure that that is zoned separately from other rooms because it will have very different heating needs. Bathrooms are zoned separately because we don't want to put the same type of heating or cooling into those spaces that we would in other living spaces. Bedrooms can be zoned separately. So in this case, we have the master suite as one room. We have bedroom 2 and 3 as a separate zone. Those could be guest rooms that are not used very often, and so we might want to keep those as a zone in itself and only choose to heat or cool those rooms when we have guests coming over. If those bedrooms were occupied, then I would suggest zoning each individually. And the benefits of that are that you can control the space conditioning based on the particular needs of the occupant. Some people like very cold rooms when they sleep, and others like a warmer room. And so zoning gives you the ability to customize the heat or cooling delivery into the space based on what is most comfortable to the person who's occupying that space. When we do take advantage of zoning, it's particularly necessary to include a properly sized buffer tank. So the buffer tank is simply a volume of water, and that is used to help reduce the number of times the heat pump has to cycle. That buffer tank is insulated, so it's able to keep that volume of water at a certain temperature for a certain amount of time. And so that means the heat pump doesn't have to repeatedly turn on and off to produce an entering low temperature that could be maintained within that buffer tank. In well-insulated and open plan houses, or if zoning is designed so that the minimum zone heating or cooling requirement is matched exactly or very closely to the minimum output of the heat pump, well, in that case, a buffer tank may not be needed. Also, heat pumps that have variable speed compressors may not require a buffer tank. So this is a general guideline, but depending on the heat pump that you have and the design of the zones themselves and the house plans, you may not need a buffer tank. If a buffer tank is not needed, then it is important to do hydraulic separation. So to use some closely spaced tees or hydraulic separator so that we ensure that we are separating the flow from the heat pump from the flow to the distribution loop. So I can't say this enough when we're talking about hydronic design considerations, that we have to make sure that we are going to be designing a system with the lowest possible entering load water temperature when we're in heating mode. The coefficient of performance, which is the efficiency of our heat pump, is highest when that ELWT is at its lowest. The rule of thumb for heat pump systems is that we want to steer away from any design temperatures that exceed 120. Now, that's for R410 refrigerant. If your heat pump uses a different type of refrigerant, then you may have a different maximum design temperature that you can use. But the general rule of thumb that applies to most heat pumps is 120 degrees Fahrenheit. Now, as we mentioned earlier, radiant floors are an excellent installation for heat pump applications because they operate best, in fact, with the low water temperatures. So we are able to keep that entering load water temperature very low and to maintain a high level of occupant comfort. So they are an excellent application for the geothermal design. Now, the types of radiant floors that are suited for geothermal applications are the heated floor slabs and the heated bin slabs. Both of these will be optimized at low water temperatures. When we're designing low water temperature radiant installations, it's very important for us to consider the R value of the floor coverings. We want to design with the lowest possible R value that we can. So this is a list of typical thicknesses for a variety of different floor coverings and what their typical R value is. You can find information like this at a number of sources. I was able to find this data from the Radiant Professionals Alliance website. So you can see we have sheet vinyl and vinyl tile, ceramic tile, and marble, and all of these materials have a very low R value. So they work really well with the low water temperature radiant installation. Maple hardwood, we have a typical R value of 0.66. That's still not bad. Engineered wood 0.75, cork at 1.18, and if we're looking at low profile wool carpet, that has an R value of 1.5. So if we want to stay as low as possible, we're looking at the vinyl, ceramic, marble. Those make excellent floor coverings for radiant installations. And then the further down we go on this list, the more insulative that floor covering is going to be, which is obviously not ideal for a radiant operation. This graph is showing how floor coverings and tube spacing affect the heat flux for a heated floor slab. So we have a variety of different lines on this chart, and they're in pairings, and each pairing corresponds to a different R value. So here the blue and the red are both for an R value of 0. So that would just be if we're painting our slab and not installing any floor coverings. We're moving up to an R value of 0.5 and increasing all the way to an R value of 2. Now the blue line represents 6-inch spacing between our radiant tubes, and the red line represents 12-inch spacing. So we're going to take a look at how this tube spacing and the R value are going to affect the upward heat flux for a variety of different delta T's. Now the delta T is the average water temperature minus the room air temperature. So for example, if we're looking at a heated floor slab that has 6-inch spacing with an R value of 0, so no floor covering, maybe just using some paint on that slab, then we're going to be looking at this blue line. Now let's say that installation has an upward heat flux of 20 BTU per square foot. What that means is our driving delta T is going to be 17.5. That means for a room to be 70 degrees Fahrenheit, the average water temperature has to be about 87.5. So let's say a supply temperature of 95 to 100. Well, that works really well for the geothermal radiant installation. We are well below our design temperature of 120. However, if we're using that same upward heat flux of 20, and now we move to 12-inch spacing with a floor resistance of 1, we're going to be over here looking at the red line for the 12-inch spacing, and we'll follow that down until we get to our 20 BTU per square foot upward heat flux. That corresponds to a driving delta T of 42.5. So to maintain that same room at 70 degrees, we need an average water temp of 112.5, which means a supply temperature of 120 to 125. So we're still within an acceptable range for a design temperature for a geothermal radiant installation. However, we have definitely sacrificed the efficiency of our heat pump. Once our entering load water temperature is climbing from, let's say, 95 to 125, that ends up being quite a big jump in heat pump efficiency. So it's very important for designers to consider the upward heat flux and how it's going to change based on the R value and the tube spacing, and what impact that's going to have on the driving delta T. We want to make sure our entering load water temperatures are as low as possible, and that means to keep our spacing as close as possible and to keep our R values as low as possible. So the general guidelines for slab on grade installations: the tube spacing should not exceed 12 inches. And even 12 inches, as we saw in that chart, does have quite an impact on the driving delta T. The slab should have a minimum of R10 underside installation, so we're not experiencing heat loss where we don't want to. The tubing should be approximately 2 inches below the surface to make sure we are getting that good heat transfer. Preferably, we would like an R value of 0. So bare, painted, or stained slab surfaces are ideal. And if you are going to install a floor covering, then make sure the R value is under 1. And even an R value of 1 can be very insulative. So keep that in mind when you're designing your geothermal distribution system, that it's going to have an impact on your entering load water temperature, which is in turn going to impact the efficiency of the system. The other type of radiant installation that works well with this type of geothermal system is a heated thin slab. Now this requires slightly higher water temperatures than the slab on grade, and that's because the slab is thinner than slab on grade floors. So it has slightly less heat dispersal characteristics, which translate into a slightly higher water temperature requirement. Now the general guidelines for thin slab installations are that the tubing should not exceed 9 inches. So now we are reducing that upper limit on the tubing because we have slightly less heat transfer capability with the thin slab. The slab should have a minimum of R19 underside insulation. And again, we want to make sure that if we are using floor finishes, they have an R value of 1 or less. And remember, the higher that R value, then the more insulative it's going to be. And when what we want is a system that radiates heat very efficiently and effectively. The other guideline is not to use lightweight concrete, always to use gypsum. Now when we're designing the radiant system, it's often the case where the heat output from the radiant does not match the heat loss of the space. So this is when we have to consider second stage heat. So this is an example of a space that has a radiant floor as our first stage of heat and a forced air system as our second stage of heat. Now, the air system can provide a fast response when additional heat is required, whereas because of the thermal mass of the radiant installation, it is slower to respond. So it provides a great base load of heat, but if we're not meeting our zone's heating needs, or we would need a faster response, then the forced air system is used to supplement that base load amount of heat. Now, typically when we talk about forced air heating, the supply water temperatures are higher than we would like to see for a heat pump application. Remember, we typically recommend, based on the refrigerant that a heat pump is using, that the design temperatures are no higher than 120 degrees Fahrenheit. Well, usually when we're talking about forced air, the design temperatures are higher than that. So we have to take special consideration in the types of terminal units that we're choosing for our second stage of heat when we're doing a geothermal application. So fan coils can be used with hot or chilled water. So it's great for a heat-cool hydronic system. But we have to remember, when we're talking about hydronic systems, the fan coils have to be sized larger to account for the lower water temperatures. Now we also have manufacturers that make low water content heat-cool fan coils, and these operate at reduced water temperatures, so the units don't have to be sized quite as large. But generally speaking, if you have an ordinary fan coil, then we have to size them larger to compensate for the lower supply temperature. Now, if we don't want to go with fan coils, what other options do we have for that second stage of heat? Well, one thing we have is a low mass panel radiator. So traditional radiators are not a good selection for a geothermal application. And that's just because they require very high supply water temperatures. However, low mass panel radiators do work well with the lower entering load water temperatures. You have to size the panels so they deliver the design space heating output using the recommended design temperature of, let's say, a maximum of 120, which is the case for most heat pumps. Now, just like a forced air system, panel radiators, because they have low water content, are also one of the fastest responding heat emitters. So we can complement our radiant base load heat delivery with a fast acting second stage of heat using the panel radiators. The key here is really that the panel radiators have to be sized appropriately. So the manufacturers will publish height, length, and number of water plates, and then publish the corresponding heat output for those parameters. So make sure to reference the manufacturers and appropriately size the panel radiators for the heat loss in your particular space. Ultra-low mass radiators have been available in Europe for a while, and now they are available in North America. So what kind of advantage do these offer over panel radiators? Well, believe it or not, they contain only about 10% of the water content that a typical panel radiator would contain. So with that reduced water content, we are able to operate at even lower temperatures and be even faster responding. These radiators also come equipped with a rack of mini fans, and these enhance the convective heat transfer at the low temperatures. Now, the fans typically only require about 2.5 watts at maximum speed and have a virtually undetectable sound level. Now, on the chart, we have shown information from one of the manufacturers of ultra-low mass radiators, and you can see we're assuming an average temperature of 110 degrees Fahrenheit. Now, this would be the lowest water temperature for this particular manufacturer, but I have seen others that have starting water temperatures as low as 95 degrees Fahrenheit. We have height in this column, and we're ranging from 12.5 inches high all the way down to 36 inches high. And then we have two different lengths, 19.5 inches and 55 inches. Now, under these two columns, we have the BTU output for that particular height at the water temperature of 110 degrees Fahrenheit. So you can see we are moving from the low end, which would be the smallest height and length, and we would have a heat output here of just over 1200 BTU per hour, all the way down to a length of 55 inches and a height of 36 inches, which is going to give us just over 5700 BTU per hour. So quite a significant heat output with very low water temperatures. So this is an excellent type of installation for second stage heat in a geothermal application. We also have low temperature baseboard now. Now this type of baseboard has larger fins than traditional baseboard with a two-pipe supply design. The fin area is about 3 times larger than typical baseboard. And at a supply temperature of 110 degrees Fahrenheit, the heat output is just under 300 BTU per hour at a flow rate of a gallon per minute. So very different from conventional baseboard that's typically designed for supply temperatures ranging from 160 to 200 degrees Fahrenheit. The fact that we're able to include baseboard to operate at supply temperatures as low as 110 means that we can actually include this type of heat terminal in our geothermal application and still offer those very low entering load water temperatures to get that maximum heat pump efficiency. So we just looked at some low temperature second stage heat terminals. Can we include these types of terminals to be on a design with a radiant installation at the same water temperature? Well, probably not. It isn't very good from a control point of view to have heat terminals that, even though they are all low temperature, they still require different temperatures. So that's what we would call a dual temperature system. Now, how can we mechanically design our system that has 2 stages of heat that will likely operate at 2 different temperatures? The answer is to include a mixing device. So a mixing device will let us control the water temperature for both of these heat terminals, for the radiant installation and for the second stage heat installation. Including a mixing device in our design when we're talking about radiant installations and second stage heat terminals is an important consideration. Typically, the radiant is going to be operating at a lower temperature than that of the second stage heat installation. So to avoid compromise, because that's what it would be if we put the radiant and the second stage heat on the same water temperature, that would be a compromise in performance. And that often leads to unsatisfied customers and complaints about comfort levels. So to avoid that, we are going to make sure that we include mixing in our system, and that will allow us to customize the entering load water temperature for the radiant as well as for the second stage heat, and make sure we're operating both of those installations so that they're providing maximum comfort. Variable speed injection is one method of including mixing in the mechanical design. There are, of course, other options such as mixing valves. But the reason we're going to be focusing on variable speed injection is because that is what the 406 house control supports. The 406 will only support variable speed injection. It does not have the ability to operate a mixing valve. So if you're designing your system and hoping to use a 406 house control because it's an out-of-the-box solution and you don't have to, triple or quadruple your control cost with DDC, then make sure that you design with variable speed injection. Now the benefits of variable speed injection are that it has a quick response. It just uses standard wet rotor pumps and it's very easy to service. However, it is limited in size. So we need less than 2.5 amps and 1/3 horsepower to be able to do variable speed injection. Now we're going to look at radiant floor cooling because there are separate design implications that exist for radiant floor cooling. There are obviously certain things we have to take into consideration that we don't have to when we're talking about radiant floor heating. So radiant floor cooling introduces a bit of a curveball as far as the design and the control perspective come into play. And we have to just make sure that we design and plan the control strategy accordingly. To understand the capacity of radiant floor cooling and also to understand its limitations, it's important for us to distinguish between the sensible cooling load and the latent cooling load. So sensible cooling loads refer to the dry bulb temperature of the space. If we are removing the sensible load, we are actually reducing the air temperature of the space. The latent cooling load refers to the wet bulb temperature of the space. So reducing the latent load refers to removing the moisture in the air. And it's very important when designing a cooling system that we address both the sensible load and the latent load. However, radiant cooling can only address the sensible cooling load. We cannot remove humidity with a chilled floor. Latent cooling and ventilation require a forced air system. And in a geothermal system, latent cooling is almost always provided by chilled water fan coils. And for that, we need the coldest water temperature available. Typically no colder than 45 degrees Fahrenheit. When we get lower than that, then we really do start compromising our heat pump efficiency. Now, just like when we're talking about heating, when we talk about radiant floor cooling and forced air cooling, these are dual temperature systems, and they should not be designed to have the same water temperature. Now, the fan coil supply temperature, like we just said, is a minimum of 45 degrees Fahrenheit. A radiant floor supply temperature has a minimum of 2 degrees above the dew point temperature of the space. And we'll talk more about the concept of relative humidity and dew point temperature in the next module when we talk about the control features of our 406 and 557 combination. But definitely, 2 degrees above dew point temperature will be well above 45 degrees Fahrenheit. This is definitely a dual temperature system where we have different needs for supply water temperatures going to the radiant system as we do to the forced air system. Without two water temperatures, it's impossible to have a well-controlled cooling system. The dew point reset temperature will make the water temperature for the fan coils too high, and thus very unlikely to satisfy the cooling loads and dehumidification set points. So what tends to happen if we don't design this system properly and we have put the radiant installation on the same water temperature bus as our forced air system? Well, either the forced air system operates at higher water temperatures, which is not comfortable, or we actually prevent the radiant installation from operating at all. So we forego the floor cooling and do strictly forced air cooling. And neither one of those scenarios is the way the system was intended to operate. So we're going to have very unhappy customers here. That's why it is absolutely critical that when we are designing a system that has radiant cooling and a forced air cooling system, that we include mixing. We have to isolate those two water temperatures. The radiant floor cooling will be subject to dew point reset, and that is essential to make sure that we avoid condensation on the floors. But the fan coils will require colder water temperature than that. So by incorporating mixing into our design, we make sure we can provide the appropriate entering load water temperature to both of those separate installations and make sure that the system performs as it was intended to do so. So it comes down to design and it comes down to control. We talked about the control strategy a little bit. As I said, we are going to focus more on the control strategy in the next module. But suffice to say for now that the control strategy is a critical part of the hydronic design. We need to make sure that when we zone our system and we implement zoning controls and system controls, that we have a way to efficiently switch between heating and cooling. Because every time we switch from one mode to the other, we're going to be sacrificing efficiency. So we want to make sure we're doing it when we need to do it, that we're not doing it too often, and that we are satisfying the majority of the zones when we do so. The control is what will tie everything in together to always maintain efficiency, to always optimize performance, and to make sure that we are operating the system the way it was hopefully designed and intended to operate. The 557 was introduced in August of 2012, and we've had great success with its installation in geothermal heat-cool applications, in particular radiant floor heating and cooling systems. And we'll talk about all those advanced design features that were developed for specifically geothermal heat-cool applications and how the 557 can optimize the performance of the overall system. The 557 offers flexible and customized zone control. It has a built-in humidity sensor, and that relative humidity measurement can be used to accurately control humidity in the space by operating humidifiers or dehumidifiers based on your preferred set points. We can also operate a fan, and for hydronic heat-cool applications, we can control a radiant floor as our first stage heat, with a fan coil as our second stage of heat in a forced air system. And then when we switch over to cooling mode, we can offer radiant floor cooling with forced air cooling through the fan coil. So a very flexible control. You can see we can also control other types of heat emitters, a convector or furnace, backup heat. But for the hydronic heat-cool applications, we are focusing on the radiant floor and the fan coil. Here's how the thermostat 557 might integrate with our house control 406 for an overall geothermal system. You can see here we have radiant floor, and that would be our first stage of heat. And it would also provide radiant floor cooling if we chose to design for that as well. Over on this other water temperature, we have our fan coil. So this fan coil, when we're in heating mode, would provide our second stage of heat. When we switch over to cooling mode, that fan coil would be our forced air cooling. You can see we have incorporated the variable speed mixing. So here is my variable speed mixing pump, and that allows me to have different water temperatures going to my fan coil as I do for my radiant installation. Particularly important for radiant cooling when the radiant is subject to dew point reset. You can see I'm also controlling a humidifier in the ductwork. We're going to look at more geothermal applications as they relate to the pairing of the house control 406 with the TechMarnet thermostat 557. This is just a teaser example, if you will. In summary, this module covered hydronic design considerations, and in particular we looked at zoning and the need for low entering load water temperatures. We looked at the types of radiant floor installations that are well suited for a low temperature geothermal application and why that may necessitate a second stage of heating. If we are adding a second stage of heating, then we have installations that operate at different water temperatures, and so that drives the need to include mixing in our mechanical design. And mixing is even more important if our design includes radiant floor cooling. We need to supplement our cooling with forced air cooling, and radiant floor cooling, which is subject to dew point reset, will require a very different water temperature than a fan coil would for the forced air cooling. So in order to maintain the integrity and to ensure the performance of our system, it's essential to include mixing in our design. And lastly, we briefly looked at the thermostat 557 to see how zone control comes into play when we're talking about the control features that are necessary for our distribution system. As always, if you have any questions about this subject matter or there's something else on your mind, please let me know and send me a message. I can't tell you enough how much I appreciate the feedback that I've gotten so far in this course. You guys have a lot of experience and background in the subject matter, and so your feedback matters to me, and it allows us to always improve the quality of our presentations. So thank you again for that. On that note, I look forward to hearing from you, and you'll be hearing from me when we get to Module 5, where we'll be looking at the House Control 406 and the TechMarNet 557 in greater detail. Thanks a lot. Have a great rest of your day. Bye-bye.